So there's two additional quantum numbers that we get from the Schrodinger equation. And just like n, the principal quantum number, they're going to give us information about the electron within the atom. The second one is the angular momentum quantum number, sometimes just given as the orbital, or what we do is we abbreviate L. Now L is always dependent on the energy level and can have values from 0 to n minus 1. Okay, so for n equals 1, L can have only one value, 0 to n minus 1, which is also 0, so L equals 0. For n equals 2, L can have values of 0 to 1, n 2 minus 1, so on and so forth. N equals 3, L can have 0, 1, and 2. This quantum number gives us information about the shape of the orbital, or sort of the shape of where we can find the most probable position of the electron within an atom. Now it turns out from your high school chemistry you may not recognize these values, but it will make a little bit more sense when we talk about the letter designation. For L values of 0, we typically refer to that as our s orbital. L equals 1 has a letter designation of P, and we call the orbitals within L equals 1 are P orbitals. Say L equals 2 is D, L equals 3 is F, and from there on out we will go through the alphabetical order. These letter designations come from properties of the emission spectra that were first being viewed when these quantum numbers were being investigated through emission spectroscopy. Okay. The third quantum number we get from the Schrodinger equation is the magnetic quantum number, m sub L. And really these can be referred to as the individual orbitals within an energy level. They are dependent on L, just like L was dependent on N. So m sub L can have values from negative L to positive L, including 0. So for instance, if L equals 2, m sub L can have values of negative 2, negative 1, 0, positive 1, and positive 2. Now one of the bigger aspects that we're going to utilize from m sub L values is the number of orbitals. So it turns out that L equals 2, which again was our D orbital. There are 5 orbitals in the D sublevel, rather. Okay. For L equals 0, which is our S sublevel, we can only have one orbital, so S has one orbital. We can say that S has one orbital. Okay, L equals 1, which is our P sublevel, can have negative 1, 0, and positive 1 orbitals. So P has 3 orbitals. Something that can be pictured a little bit more graphically on this slide. Okay, so here we have first 3 energy levels, n equals 1, 2, and 3. So you can see that if n equals 1, L can only equal 0. And if L equals 0, we only have one orbital, and that of course would be our S, m sub L equals 0 orbital. Okay, we use all 3 of these quantum numbers in conjunction, so this would be our 1s orbital. N equals 1, L equals 0 orbital, or 1s. Okay, if n equals 2, we know that L can equal 0 or 1, and so we have 2 sublevels, S and P. And of course, S can have 1 orbital, P has 3. And then if we finally look at n equals 3, L can have 0, 1, or 2 values. So we have S, P, and D sublevels within n equals 3. Okay? And then of course, there's corresponding orbitals associated with those sublevels. Okay? Now, if we go back to our Schrodinger equation and discuss what we reference as the orbital if we plot distance from the nucleus, r, as a function of our wave function squared, psi squared, what it looks like is that the probability of finding the electron in our 1s orbital increases as we go closer to the nucleus, and of course decreases as we get further from the nucleus. If we plot this in 3 dimensions, what this looks like is a sphere. And of course these are all the probabilities, so there's lots of different calculations for the Schrodinger equation. Each of those corresponds to a dot or a probability of finding an electron. So you can see that the density increases as we go into the closer to the nucleus and decreases as we go further away. If we turn the probability density plot into a radial probability density plot, if I can say that, you get something that looks like that. Now, as we saw previously, the probability of finding an electron increases as we get closer to the nucleus, but of course the volume of spheres gets smaller and smaller as you get closer. So even though the probability of finding an electron in that sphere very, very close to the nucleus is chi, the volume of that sphere is low, and so which causes the radial distribution function to decrease as we get closer to the nucleus. And so this is what most of the time we're going to look at, is the radial distribution function. What it shows is a maximum at 52.9 picometers, and that's usually referred to as can be used as an indicator of the radius of atomic radii. Okay. If you go to higher energy levels, so as we take a closer look at the probability density plots for the s orbitals in L equals 0, of course, we can look at the higher energy levels, n equals 2 and n equals 3. We can see that the shape of the orbitals is still very much the same because they're both s orbitals. Both of them are spherical in appearance. As you can see, there is one big difference as you go to higher energy levels for L equals 0 s sublevels, and that is the appearance of nodes. You can see that for the 2s orbital, there is one node, which we can see down here, and that is an area where there is virtually 0% probability of finding an electron in that space. In the 3s orbital, we can see that there are 2 nodes appearing, and again, areas where there is 0% probability of finding an electron in that area. This will come into play when we talk about degeneracy, or the energy of sublevels within an energy level. And a general rule of thumb for energy levels, there are usually n minus 1 nodes. Okay, so for the 1s orbital, 1 minus 1 is 0. There's no nodes in the 1s orbital. 2 minus 1, there's 1 node in the 2s, and then 2 nodes in the 3s, so on and so forth. If we take a look at the p orbitals, we can see that they're very different in shape. They have a very characteristic pear-like lobe-shaped probability density. Here you can see the radial distribution plot. And again, what we can see here is information about the m sub L values. Again, they can have any value from negative L to positive L. So for L equals 1, for the P, we have L equals m sub L equals negative 1, 0, or positive 1. And so we can see that there's 3 orbitals. And that gives us information about the geometric position of the orbitals. Each of the p orbitals, in this case 2p orbitals, we can see that there are 3 different geometric orientations to the orbitals. You can see that this one, the orbitals appear on the x-axis, For this orbital, they appear on the y-axis, and then on this orbital, they appear on the z-axis. Pictured here are the 2p orbitals. The only difference for the higher energy levels, of course, 3p, 4p, 5p, they would have the same shape. There's 3 of them, but of course they would be larger, higher energy, further away from the nucleus. Here we have the probability density plots for the d orbitals. And so we can see that d, of course, L equals 2. So we can have m sub L values of -2, -1, 0, +1, and +2 or 5 different orbitals. And again, they all take a little bit different geometric position in 3 dimensions. And finally, we have L equals 3, the f orbitals. So if L equals 3, we can have -3, -2, -1, 0, +1, +2, and finally +3, 7 orbitals in the f sublevel. Again, a slightly different appearance because of the different sublevel, but again, here they are.